Okay, we've looked at limits that we can evaluate using some algebra. Today we're going to use some trig to do limits. But before we do that, we need to look at a special theorem that's useful for evaluating limits. It's called the squeeze or the sandwich theorem. And it's aptly named, as you'll see. So here's what it says. It says if you have three functions and they behave in this manner, f is less than or equal to g, which is less than or equal to h, whenever x is near some number a. So in other words, you have three functions and they are clearly in order. One is always larger than the other two and one's always in the middle. Okay? And you are told, or you know, that the limit as x goes to a of f is the same as the limit as x goes to a of h. Let's call it k. Okay, so in other words, these two functions f and g have the same limit at a. Well, then it makes a logical sense that g would have the same limit at a, because g is sandwiched or squeezed between f and h. It makes a lot more sense if you look at a picture. So let's say that this red function is h, and this black function is g, and this blue function is f. Okay? So in this picture, this interval, which it looks like to be negative 0.6 to 0.6, it looks very clear to me that f is always smaller than g, which is always smaller than h. So these three functions meet the initial criteria. Now, if we say, let's look at x equals 0, so in other words, let a be 0, and it looks to me that the limit as x goes to 0 of f of x is equal to 0. And it also looks to me like the limit as x goes to 0 of h of x is 0. All right, we're then allowed to conclude by the squeeze theorem that the limit as x goes to 0 of g of x must also be 0. And we could do that even if we did not have the graph of g in this picture. Okay, so g's graph could not even be there. As long as we were told that this was true, then we could make that conclusion. So the picture, I think, helps it make sense. Let's look at an example where this would be applicable to us. So here are three functions, f, g, and h. We are asked to find the limit as x goes to 0 of x times the arctangent of x. Okay? Now, if we try to do a plug-in, here's what we get. We get 0 times undefined. Okay? Because you have the arctangent of 1 over 0, which is undefined. So this limit, at the moment, cannot be evaluated. We can't say it's 0, and we cannot say it's undefined because it's not just a 1 over 0 problem. You also have 0 out in front here. So this is a question mark at the moment. We can't just evaluate this by methods we've already seen. Now, suppose I tell you that the absolute value of x is less than or equal to x times the arctangent of x. Okay, arctangent has the two symbols, either tangent with a -1 exponent or arctan, either way. And that's less than or equal to, which is x to the 2/3. Okay, and I'll say that that's true on the interval -1/2 to 1/2. Okay? Now, 0 is on the interval -1/2 to 1/2. So if we can squeeze this function between two limits that are the same, we'll know what the limit is. So let's take a look here. What is the limit as x goes to 0 of absolute value of x? Well, you do a plug-in and you get 0. What is the limit as x goes to 0 of x to 2/3? We do a plug-in and we also get 0. So you have two limits that are 0 with a function that's squeezed in between. And even though that function is not defined at 0, we can conclude by the sandwich theorem or the squeeze theorem that the limit of our function that we were looking at, which is x arctan 1 over x, is also equal to 0. So very useful theorem when we have a function that's undefined at the limit point. Okay, and that should have been a 1 over x. I apologize for that. You'll get a chance to use this theorem from time to time. Any limit of the form sine of stuff over stuff, if the limit has stuff going to 0, that limit will always be equal to 1. And for better or for worse, we have given this limit the nickname Waldo. Because when you find Waldo in the Waldo books, you scream, "I found Waldo." Okay, we need to know what Waldo looks like. Well, in the books, he's got blue pants, he's got a red and white horizontal striped shirt, glasses, and this silly hat that he wears. Okay, well, in trig limits, we're looking for limits of this form. Sine of stuff over stuff, the limit as stuff goes to 0. If we see that, we know we may replace it with 1. All right, what am I talking about? Let's do some examples. Okay, we're looking to find Waldos in these two examples here. Notice first, if we do plug-ins on these two limits, we get tangent of 0, which is 0, over 0. So this is indeterminate. We don't know what the value is. We've got to do some more work. And over here, we're going to get 1 minus the cosine of 0, which is 1. So 1 minus 1, 0, over 0. Also indeterminate. We got to get busy. We can't do algebra because these aren't algebraic expressions. We got to do some trig stuff, and we have to be looking for Waldo. So what can we do? As a trig student, I'm enticed, since I'm looking for sines over sine of stuff over stuff, that I can convert a tangent x into sine x divided by cosine x. All right, that's all over x. And I need to be able to handle in this course fractions of the form a over b all over c. Okay, and understand that that becomes a over bc. So this becomes the limit as x goes to 0 of sine x over x times the cosine of x. All right, I can now see sine of stuff over stuff, and the stuff is going to 0. But I want you to clearly show me that you know what you're doing. So we're going to use our property of limits that says the limit of a product is the product of two limits. And I want you to separate out the Waldo from the rest of the limit. So here's what I'll do. I'll take out the part that's Waldo, or that I think is Waldo, and then I'll leave over what's left, 1 over the cosine of x. Now let's verify that this is Waldo. Okay? Do I have sine of stuff over stuff? I do. Is the stuff, which is x, going to 0 in this case? The answer is yes. So this first limit here is what we would consider a Waldo, and we know that Waldo is equal to 1. So that's now canceled out. We don't have to worry about it. What do we have now over here? We have a plug-in situation. We have 1 over the cosine of 0, which is 1. And so our answer to this first limit is 1. All right, now what about over here? Indeterminate, so I have to do some work here. In the trig world, when I see 1 minus or 1 plus a trig function, bells and whistles have to go off in my head that I'm probably thinking conjugates if I'm using identities. So the first thing that pops up in my mind is to multiply top and bottom, numerator and denominator, by the conjugate to 1 minus cosine x, which is 1 plus cosine x. What does that create for me? Well, it creates the limit as x goes to 0 of 1 minus cosine squared x over, I'll leave the bottom factored, x times 1 plus cosine x. Okay, bells and whistles should be going off my head. 1 minus cosine squared x is a Pythagorean identity, and it is equal to sine squared x. Bottom remains x times 1 plus cosine x. Still taking the limit as x goes to 0. Now, I'm starting to see a Waldo develop here. I need to see a sine of stuff over stuff. Sine squared x means sine x times sine x. So there's really two sine x's being multiplied in the numerator. I'm going to take one of those out along with the x and split this limit into two pieces. What's left when I take off sine of x over x? I have the sine of x over 1 plus cosine x. This first limit is Waldo. Sine of stuff over stuff, and the stuff, which is x, is going to 0. So that limit's equal to 1, and I'm now left with what's over here. I do a plug-in. I get the sine of 0, which is 0, over 1 plus the cosine of 0, which is 1. So I have 0 over 2. So this limit is equal to 0. So again, indeterminate forms, this one ends up being 1. This one ends up being 0. Waldo is the key in both examples to evaluating the limit.